Right, so today's lesson, I'm going to give you both a voice note and a video. Okay, because we're looking at the idea of refraction. Okay, now refraction, as we've learned before, is essentially the bending of light when it goes from one medium to another. Okay, and it depends on the idea of the refractive index. Now, the refractive index is the ratio of the speed of light in air or a vacuum to the speed of light through another medium. Okay, so that's in your textbook after refractive index. It's the same thing in your exam guideline as in your textbook. So refractive index is given to us by the equation n is equal to c over v. Okay, now n is the refractive index. C is the speed of light in a vacuum. So the speed of light in a vacuum is 3 times 10 to the power of 8 meters per second. Remember, that is always going to be given to you at the back of your textbook. In your test. And v is the velocity of light in the medium, or the speed of light in the medium. Okay. Now, obviously, as you can see from the equation where n is equal to c over v, the speed of light in the vacuum will always be the bigger number. The speed of light in the medium will always be a smaller number. So our refractive index will never go below 1, actually. So if you are getting a refractive index below 1, then we have a problem, because that means we're somewhere where the speed of light is going faster than the speed of light in the vacuum, which is impossible currently, according to our current model of physics. So if we carry on down the page, you'll see there's a table of different refractive indices, and you can see from going from air, which is essentially very similar to a vacuum because of the density of air is quite low, which is 1, all the way to something like diamond or cubic zirconia, which is actually going to be very, very high in the optical density. Diamonds are not necessarily very dense objects. They're not going to be like lead or anything, but it is very optically dense, so it will bend light very easily, or very, very well. That is the reason why diamonds are prized for their beauty and their sparkliness. If you have a diamond close by, you can look at it and see how well it will split light into its different colors. That is the reason why the reason why it splits those lights into different colors so easily is because of its refractive index. Okay, I'm assuming most of you remember that due to refraction, light can be split into different colors. It can disperse, right? You learned this a little bit in grade 8, where white light can be broken into the multiple different colors. Now, essentially, the higher the refractive index, we're bringing it back to this work, is that the higher the refractive index, the more easily light can be dispersed. Okay, so if we talk about how light can be dispersed in ice compared to water, light will disperse the best and easiest in diamond. Okay, so there is an example of finding out the speed of light in a substance. I don't think I need to go through that with you. You can read through that. It's fairly self-explanatory. Now, the one thing I wanted to do, and it might be more useful to go through it in the video, but obviously if you are listening to the voice notes in the beginning, the idea is that you can download the video or not. I will upload it to YouTube, so it will go down to a much lower resolution. Okay, but the idea is that we're going to look at the diagram of refraction. Okay, now a diagram of refraction, I'm going to go from left to right, whereas your book goes from top to bottom. Oh, actually, let me just follow the book. Okay. First and foremost, if we have an air glass layer. Light will be incident at a specific point. Once that light is incident, we can draw a normal, and we measure according to the normal the angle of incidence, so theta I. Now, it's going from a less dense to a more dense medium. So if it's a less dense to a more dense, it will bend towards the normal. So that is our theta R. Okay. Now, this is refraction. Okay. So we have the incident ray with the angle of incidence. Then we have the refracted ray as well as the angle of refraction. I'm sorry, this is very, very small. Okay. Now, in your book, it shows how the light can pass through the object. It can go from air to glass back into air. So that means our refracted ray will then be incident again to another surface, an air-glass interchange again. So at this point, we have now another angle of incidence. Okay, so we have now another angle of incidence. But now this is going to go from glass to air. That means our light will be refracted once again. Okay, now once we have another form of refraction, something we need to keep in mind is that our first angle of incidence and our last angle of refraction are going to be equal. Okay, why? Because if we have a glass cube or a glass prism, the two sides are going to be parallel. So according to the law of parallel, they're alternate in angles. Okay, now you can use that for almost every single object. Okay, there is another example of a glass prism, which is a triangular prism. Okay, and that triangular prism can be explained exactly the same way. Okay, always remember, angle of incidence is an angle of reflection, and angle of refraction are always measured according to the normal. And then you have in your textbook some definitions regarding the normal, the angle of incidence, and the angle of refraction. Okay, so let's pretend we have an air-water interface. Okay, this is going to be easy to see in the video. If we have light that is incident to water, we know that water can also reflect light. So if we talk about reflection, then our angle of incidence is going to be equal to the angle of reflection. Okay, so that's because of the law of reflection. But now let's pretend that the light is going to refract into the water. Because it's going from a low density to a high density, it will bend towards the normal for an angle of refraction. This is the reason why if you are lying in the bottom of a pool, holding your breath obviously, that when you look straight up from the bottom of the pool up to the surface of the water, you tend to have this circle around you. It's due to the fact that your light from specific angles will only be able to reach you. Okay. Now you can see this effect. You can see refraction at work every single day. Now you just need to notice it. You notice it in your water bottle. Notice it in your clear plastic. Notice it in the glasses. Notice it in your bathtub. Alright. This is where we talk about refraction. Okay. Now, I know most of you are fairly quiet on the group, but please make sure to ask me questions. I have no idea if you guys understand this or not, so you better actually say something. Otherwise, I'm just going to assume you all understand it. Yeah. All right.